Hi everyone, in this video we're going to just quickly cover Kepler's laws and then go through the equations of planetary motion. Kepler observed our solar system and determined these laws from its observation. However, they do apply to any small bodies orbiting a larger body. Alright, the first one just says that the orbits of planets are ellipses and the sun is at one focus. So definition of an ellipse is a shape that has two foci, all right, where a circle only has one focus. Kepler's second law says that the line drawn from one planet to the sun sweeps out equal areas in equal times. Basically saying that the object will travel faster when closer. So the object will travel that distance. So you can see that the distance is greater. If it's in the same amount of time, the speed will be greater. It's closer to the sun, and it gets like slingshotted around and thrown out into space, and then it'll slow down, and in the same period of time, it'll just cover less distance. So it speeds up, slingshots around, gets flung out into space, speeds up as it gets closer. And we're going to see that there's an equation for how fast the object is orbiting, depending on the distance. And this is the last one. It's the only one that's mathematical. And it's just saying that there's a ratio for the time. Whoa. So it's the time squared for planet A over the average distance cubed for planet A is going to be the same for every planet orbiting the sun. This is the only mathematical law that we're going to use from Kepler. The equal times and equal areas is mathematical, but we're not going to look at that in this class. Alright, so now we're just going to look at the equations for planetary motion. Alright, here we have a planet orbiting the sun, and what's causing the planet to stay in its orbit is gravity. And the velocity of that planet is going to be tangential to the circle. So if the sun somehow vanished, the planet would fly in a straight line forever. This is circular motion, so we're going to use the concepts of circular motion. We know that if we add up all the centripetal forces, and it's going to have a centripetal acceleration in the direction of the unbalanced force. Since this is a circular orbit, we know that there's always going to be an acceleration. Now, the only force acting on the planet is gravity. And we know that the universal law of gravitation is equal to this, where big mass is going to be the mass of the larger object, little m is going to be the orbiting object. And of course, r is the radius of the circle. You can see that we have the little mass on each side, and solving this for the centripetal acceleration, we get this relationship. And let's say we went to the sun, and we had the radius of the sun, and we plug that into this equation. So we are now standing on the surface of the sun. What this centripetal acceleration would be the gravitational constant. So if we used the mass of the Earth over the radius of the Earth squared, this one would equal 9.8. So that is the first equation for planetary motion. And all it is a combination of Newton's second law for circular motion and the universal law of gravitation. Let's do it again. Sum of all the forces equals ma. Fg is g big M, little m over r squared. Okay, so now what we're going to do is solve this equation for the speed that this planet would need to orbit at that distance r. First thing is, the only force acting on the planet is Fg. Make those substitutions. And what we're going to put into this equation is V for circular motion. And we're going to put V in some relationship that is equal to AC. So it's that centripetal acceleration relationship for V squared over R. Mass cancels again. So notice the mass of the smaller object has canceled out twice in the last equation and in this one. Rearranging this for the speed, we get this. Now notice the r's cancel out there, so we get rid of the r squared. And this is the orbital speed. The speed necessary for any object, doesn't matter the mass of this object at all, to orbit at that location away from the sun. It's the mass of the sun that matters, or the mass of the larger object. So this works for the orbital speed of a satellite around the Earth. So if we want to put a satellite some distance away from the Earth so it doesn't collide with another one, we have to give it a certain amount of speed to remain in that orbital radius. And it's the mass of the Earth that's going to determine that radial distance. All right, we're going to do it again. However, instead of the velocity, we're going to put it in terms of the period. All right. First substitution is the only force acting on the planet is Fg. So you make that substitution in. Now substitute centripetal acceleration out for something in terms of period. So that's the equation we would use. I forgot to cancel out the masses up here, so we can cancel out the little mass. Little mass doesn't matter, only the mass of the larger object. And I'm going to manipulate this, and I'm going to leave it with the squared. All right, so if I wanted to solve for the period, and I'm going to solve for a different relationship. I'm going to leave the periods and the distances on one side. All right, and we get this. So remember, I have r here. When that jumps down, that gets cubed. And just did the rest of the cross multiplication. This relationship is Kepler's third law. And Kepler's third law says that the ratio of the periods squared over the mean distances cubed is the same for all objects orbiting the sun. So when we look over here, if this is for the Earth, and we had another one for Mars, remember they were all equal to each other, right? That means that these numbers are constant. so that this number has to be constant. 4 is a constant, pi is a constant, g is a constant, and if we're looking at every object around the sun, that's going to remain constant. If we change it to the Earth, so every satellite is orbiting the Earth, it's still going to have its own constant square of the periods to the cube of the radius relationship. Okay, those are the 3 equations of planetary motion. We can solve for the gravitational constant g at the surface of any planet using the first relationship, the orbital speed needed to remain at a certain location with the second, and look at the length of time that a year would be for a planet orbiting the sun. Because remember that the period is the time that it takes to go around once. That would be equal to 1 year. You have to be able to prove those equations. I do not think that they are on your equation sheet at all, but it is just a combination of these 2 relationships, that there's one force causing the centripetal motion, and that force is gravity, and it's the universal law that gets substituted in. And depending on what you plug in for AC, will give you the 3 different types. All right, that's it for this video.